Okay, so let's start. So this is the course Introduction to Electronics and lecture number 6. And we are discussing techniques for circuit analysis. And in the last lecture, we had seen two tools that can be used widely for circuit analysis. One was a nodal method of analysis, and the other one was mesh method of analysis. So today we'll see two more techniques that can be used for circuit analysis. And so let me start by, before we discuss those techniques, let me start by something which is in a different context altogether. And these are the 5 laws of library science by an eminent librarian, S.R. Ranganathan. And what I want to emphasize here is the first law of library science: books are for use. Now, this is obviously self-evident, but many times we violate this basic rule. Libraries violate this basic rule. They purchase books and they put it in an obscure somewhere higher up, and the aim becomes simply stocking of books. While this first law is telling us that books are for use, and therefore they must be arranged and so that they're easy to find and they're easy to be used by the patrons of the library. And anyway, so the reason why I'm putting this is there are some simple rules, simple principles, which are sort of self-evident when we talk about it, but in practice we often forget it. And that's true of analysis also. So many times when we are analyzing something and the goal becomes determining a particular number, in the context of circuits, determining a particular current or a particular voltage, and all discussions then revolve around determining those numbers. So I want to re-emphasize, just like books are for use, well, analysis is for understanding. So we should not forget this larger goal that when we are analyzing something, the numbers that we get for currents and voltages are a means to the greater problem of achieving understanding, achieving insight into how the circuit operates, right? So let's not forget this while we analyze circuits, while we determine currents and voltages, that this is the larger goal of our discussion. Okay, so if you recall, we had discussed this particular example in one of the earlier lectures. We said, suppose you have a strain gauge and you want to convert the strain. So it's basically a resistor which is sensitive to strain, and you want to convert the change in resistance as a result of strain into a display on the LCD. And we had said that we could make a Wheatstone bridge, and the signal from the Wheatstone bridge for as a result of the strain may be small, so we amplify it. And then we may do some other signal conditioning, convert the analog signal that we have into digital signal, and convert it into appropriate form so that it can be displayed on the LCD that you see over here. And as part of this, we saw that we have a Wheatstone bridge, and we have a Wheatstone bridge here. And in general, because we are applying strain, and also in one of the problems, or in general, we know that the resistors, even if you choose them 120 ohms and 120 ohms, they will be a bit different from 120 ohms. And temperature also causes a change in the values of the resistors. So in general, these resistors R1, R2, R3, R4 will not be the same. And therefore, our interest is in finding out what is the voltage across R5. And because this is the voltage that goes to the amplifier and eventually is displayed on the screen here. So we need to analyze this Wheatstone bridge in the general case where we have all these 5 resistors that are there here. Okay. All right. So if we apply the methods that we talked about, let's say a nodal or a mesh, I got one student to do this analysis. And this is what he was, these are his, his sheets of how he worked it out. So this is page number 1, this is page number 2, this is page number 3. And finally, the student got the result here. You put it back on the page 1 here. This is the result. And he told me that he's not really sure. Quite likely there's going to be an error in it. He wasn't sure whether the answer is correct or not. Well, in this case, the answer was correct. All right, so he was careful in doing the analysis. Basically, he followed a mesh method, obtained three equations that you see here in terms of I1 and I2 and all that, and then manipulated it to get the answer. So let me write the answer out here. Okay, so V0 is this big expression that you see here, right? Now, that's where, we started this particular discussion by saying analysis is for understanding. So we've derived an expression, V0 equal to so much. And if we plug in the values of R1, R2, R3, R4, and R5, we'll get a number. We'll get a number for V0. And if we are careful in putting all the numbers here and adding them up and dividing it, we'll get the right answer. So that way, this result is useful. It will give us a number. But what can you understand from this particular result? So let's ask that particular question. How exactly does VSS depend on R0? Or what is the dependence of V0? Sorry, what is the dependence of V0 and R0? Or what is the dependence of V0 and R2? Well, these are all there in this expression, but they're implicit. They're implicit. And what if I told you that I could analyze this particular circuit not using the mesh or the nodal, but through another method and obtain this particular expression. V0 equal to VSS, R2 by R1 plus R2 minus R4 by R3 plus R4, R0 is here, R1 parallel R2, parallel combination, which means R1 into R2 divided by R1 plus R2. This is R3 parallel R4, meaning R3 into R4 divided by R3 plus R4. What if I told you that V0 can also be expressed like this? And both of them, if you plug in the values of R1, R2, all the resistors, and value of VSS, you'll get the same answer. So quantitatively, they are the same. The expressions they are the same. But in terms of our ability to understand the circuit through the expression, well, these are quite different. I would like to say this is a highly disordered expression. Disordered expression does not provide insight into the roles of different components, and it doesn't do that. Is R1, the role of R1 same as role of R3? Well, it's not very evident here. Of course, you can find it out, but it's not evident here. On the other hand, this expression that you see here, we call it a structured expression. There's a structure in it. It's not a flattened, all terms in the denominator are all, each one of them has three resistors and it's a flattened out term. Well, this has a structure in it. And that reveals the role of each element. It reveals it's more evident that, look, R1 is in parallel with R2, R3 is in parallel with R4. So it reveals the role, the importance of it. Okay, so we'll come back to that. So this is a structured expression that reveals the role of each element in a more explicit manner, helps you. In fact, the way the expression is written, it indicates the way the circuit works. In fact, as you can see here, the first term R2 by R1 plus R2, there's a voltage divider here, R2 and R1 here. There's an R3 and R3 plus R4 here. There's a voltage divider here. And so the expression includes within it the structure of the circuit. We will see that expressions like this will help us understand how each element contributes to, let's say, the output voltage here. So, and besides, we'll see that the methods obtained or methods used to obtain expression like this are less error prone and often simpler in terms of or would take less time to arrive at a result like this here. Let me give you another example here. Here is another circuit apparently looks simpler, R1, R2, R3, R4, R5, and R6, and our goal is to find out what is V0. And we could do a mesh analysis and the expression comes out here. V0 equal to VSS, R2, R4, R6, and a long expression here. Again, you will get the answers. If you plug in the values of all the resistors, you'll get the value of the voltage here. but doesn't give you much insight into the roles again of different components that are there here. And it's difficult to simplify the expression. If we give you the values of the resistors here, and we would like a simpler expression that tells us which terms are more important than the other, this expression doesn't help in that particular process here. All right, so what we are doing is, what we are saying is mesh and nodal analysis are brute force techniques that are not only time consuming and error prone for us to use, but also yield unstructured expressions that are often unsuitable for gaining insight into the operation of circuits or modifying or designing them. These mesh and nodal analysis will give us an expression. The expressions are useful for calculating a number, but in terms of insight, well, they're often very poor in that. And as we'll see, these techniques are more suitable for a machine, for a computer. The algorithm is very well defined. You can code it, and you can use the computer to implement the algorithm, and it will give you the result. But for us humans, these techniques are not as suitable, especially as things become a little bit more complex. Okay, so what we are looking for is, we need techniques that yield relatively simpler structured expressions. Structured expressions, why? Because they will help in revealing the role of different components. And we are also looking for techniques that require less effort and are less error prone. So we are asking for lots of things. We are asking for a simpler expression that gives us more insight, requires also less effort, and is also less error prone. And so let's see, how one may achieve something of this kind here. Okay. All right. So one of the methods that we use to achieve or to simplify our analysis, and also you would see that it results in structured expression, is what I would like to call it is analysis using a reuse methodology. So the idea is very simple, that do not carry out analysis from scratch. All right, so very often the tendency is, given anything, we start from first principles. Well, when you start from first principles and try to reach your goal, often the analysis will become time consuming and will become complex. If you want, and also likely to be error prone from first principles, because somewhere or the other it's possible that you may miss a term or write it up wrongly in the next step. Things like that happen. On the other hand, if you use, so the idea is, don't analyze things from scratch. Well, what you do is you analyze, remember, and reuse. So the idea is that there are there are results or there are circuits that you've analyzed before, and you remember the results of those particular circuits, and you reuse it at different places. Now, this principle of analyze, remember, and reuse, you've all used before. Example, we do not carry out multiplication from scratch using repeated addition. If you're asked to multiply 34 into 3, well, you don't, for example, the principle that we use for understanding what is 3 cross 4 is 12. We used, these sticks with 3 sticks and 4 times, and then you count it out and you say it's 12. Well, you don't use that first principles method of repeated addition to apply to 34 cross 3. So what did we do? Well, in fact, if you use this kind of a method, the method that you use for 3 cross 4 is equal to 12, if you apply to 34 cross 3, well, you will end up in a big problem. So you cannot carry out complex multiplication with ease using the first principle here. The principle that you use to understand 3 cross 4 is 12, you can't apply it to 34 cross 3 here. It will become too tedious. So what did we do? Well, we were all made to remember multiplication tables. 4 cross 1, 4 cross 2, 4 cross 3, 4 cross 4, 16. We all remember, these multiplication tables. These multiplication tables, how do you understand 4 into 2 is 8? By this method here. But then once you do it, once you understand 4 cross 2 is 8, you don't always do this, right? So you remember this particular result and you deploy it, right? So memorize multiplication table, and then we used it again and again at different places to carry out complex multiplication. So similarly, we are saying perhaps don't analyze circuits using first principles. Don't apply KVL and KCL. There are times when you may have to do it in a new situation. But in general, if you can, don't apply KVL and KCL directly to every circuit. See whether there are results that you can remember and reuse. Just like the multiplication table, you use it to do complex multiplication. We are saying use a result of some circuits and use it to analyze more complex circuits here. Okay, so let's see this particular principle in action here. So you've all seen this. If we have 3 resistors in series here, and 3 or more also, so we have R1, R2, R3. We know that between these 2 terminals, A and B, we could replace these 3 resistors by a single resistor here, which is R1 plus R2 plus R3, one equivalent resistance, R1 plus R2 plus R3. Well, how did we obtain this? Well, so in what sense are they 2 circuits the same? Well, as far as the terminal current voltage characteristics are concerned. So if I look at it from the terminal, if I apply a voltage VAB, a current IA will flow. Well, if I apply a voltage VAB, the current IA will flow here also, provided R equivalent is R1 plus R2 plus R3. So in that sense, in terms of the terminal current voltage characteristics, the 2 circuits are equivalent. Now, please remember when we use the notion of equivalent circuits, remember what they are equivalent, the sense in which they are equivalent, only in terms of terminal current voltage characteristics. This has 3 resistors and this has 1 resistor. So for example, in terms of cost, this may not be the same as this one. 3 resistors may cost you more than this. Well, 3 resistors together may weigh more as compared to 1 single resistor. So, you know, we're talking only in terms of equivalence, in terms of terminal current voltage characteristics, okay? In that sense. So how did we get this result? R equivalent is R1 plus R2 plus R3. Well, through KVL and KCL. So for example, if we apply KVL to this particular loop here, we write VAB equal to IA into R1, IA into R2 plus IA into R3. We have implicitly used KCL because the same current is flowing in all these elements here. We've used KCL there. VAB is IA into R1 plus here. And we can rewrite this as IA into R1 plus R2 plus R3. Well, in this circuit is simple Ohm's law. VAB is IA into R equivalent. So if you want these 2 circuits to give you the same current voltage characteristics, it's obvious for the same VAB, if you want the same IA, then we find R equivalent is R1 plus R2 plus R3. So we derived this particular result using KVL and KCL. And but then the idea is that wherever you see now series connected circuits, let's say several resistors, well, you can combine them into 1 single resistor. So that's a result. For example, we would like to reuse it wherever we find it is convenient to simplify circuits and simplify analysis here. So a result which has been derived using KVL and KCL, but we are not going to, every time we see R1 and R2 and R3, we are not going to apply KVL and KCL again to analyze that particular part of the circuit. Well, we'll replace it by this particular result here. Okay. So once derived, this is a useful result that can be reused at many places. So that's what we are talking about. Don't analyze circuits from scratch. Reuse a result, reuse certain results at places where you find that you can apply them. Well, the other one you're all familiar with. If I have 3 resistors in parallel, again, the same process, I can replace it by 1 single resistor here. 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 here. And you know, so in this case, for example, we apply Kirchhoff's current law here. So the current at this particular node, let's say IA entering, will be equal to VAB by R1 and VAB by R2 and all that here. In this case, the current IA is obviously, and we can write this here, and in this case, VAB by R equivalent. And if terminally, from the terminal side, both of them are equivalent, then we get this result here, right? So again, once you derive this result, this is a useful result that can be reused at many places. So the idea is that wherever you see parallel resistors, well, take advantage of this particular one. Don't go ahead and apply again a KCL to that particular part of the circuit. If you try to do that, well, your circuit analysis will become more complex and you'll take more time and likely to be commit errors also. Now, this result, it has been derived and you've verified it, you've used it, and so you're sure that there are no errors in this particular part of the result here. Okay, So that's how analysis becomes less error prone when you use results which have been pre-derived, pre-verified before. So when you deploy such results, the chances of error become less. All right, so the other one related to that is the concept of voltage division. So when you have a voltage here and you have several resistors connected in series, the voltage of course gets divided amongst these three resistors, and in general the voltage across jth element will be the resistors, jth resistor divided by sum of all the resistors here, right? So in this case V2 will be equal to Vs R2 by R1 plus R2 plus R3 here. So that's the concept of voltage division in a series connected series of elements here, right? Again, we have derived it. You can derive it from first principles, but use it wherever you can find that this is applicable. Similarly, counterpart to that is the current division. The total current flowing into a parallel combination of resistors will be divided amongst them. So if you have a current here, it will divide between R1, R2, R3. And the current, let's say, flowing in R2 would be equal to the current which is dividing multiplied by this expression here. And a simpler one where you have only two resistors is often useful, we'll find. I2 will be equal to Is multiplied by, since it's I2, the resistor here is R1 plus R2 here. Okay, so a useful result derived using your KCL and KVLs, and can be deployed at many places. Okay, so let's come back and see how we use those results here. Okay, how do we analyze this particular circuit using series and parallel resistors and voltage and current division. And let's see, when we analyze this particular circuit, what kind of a result do we get here? Okay, so our strategy is, note that we have to find out V0, expression for V0. So the idea is that this particular circuit, VSS, will cause a current ISS to flow here. This current ISS will divide here between R2 and the rest of the circuit here. So current I3 will flow here, let's say. This current would further divide, some current I5 will flow here. And the same current I5 flows through R6. So V0 will be equal to I5 into R6. So we could start by analyze this particular circuit by finding what is ISS, then what is I3, and then what is I5, and then multiply it together to get V0. So to find out ISS here, well, this whole part of the circuit can be combined using series parallel into one single resistor here. So we reuse our series and parallel results here. So note that the equivalent resistance R5 and R6 are in series here. Well, so we write in series here. They're in parallel with R4, so we use this parallel in R4. The whole combination is in series with R3. Fine, we write R3. Then the whole thing is in parallel with R2, so we do that in parallel with R2. And the whole thing here is in series with R1, so we write it in series with R1 here. And therefore, ISS, the current here, will be VSS by R equivalent, which is this expression here. All right, so now this ISS will divide between I3 and, some current will go in this here and some current will go here. We could look upon this whole thing as one single resistor using series and parallel. So we can use the concept of current division, right? So if you have a current here, in this case, the current dividing between two resistors here. So in this case, ISS is dividing between R2 and another resistor, which is a combination here of R3, R4, R5. Okay, so we can write it as I3 will be equal to current going here would be this resistor R2 divided by the sum of the two resistors here, R2 plus the resistance of this particular part here, which is R6 plus R5 parallel R4 series R3. So we write this down here. And then now this current I3 is dividing between this branch and the remaining branch. So we can apply it here. I5 will be equal to I3, R4 divided by R4 plus the net resistor here, which is R5 plus R6. So we get I5 here. And V0 will be I5 into R6. So let's put all these results together and we get this expression. V0 is VSS by this expression here into R2 by this expression here, R4 by this expression into R6. All right, so we can already see that there is a lot of structure in this particular expression. So let's compare the two. Also, note that we did not use KVL, KCL explicitly. And in fact, we could, with a little bit of practice, you can write these particular results down in one single step, by looking at it. So, it leads to solving circuits by inspection. You see a circuit like this and you could go and write this, you could do it in your head, these steps, and you could write it down, what the value of the output voltage will be, okay? All right, so let's compare the two expressions. So we have an expression like this here that we obtained, let's say, through the mesh analysis. And we have an expression here that we obtained using our reuse methodology, using series, parallel resistors and current division principles. So we do that and compare the two expressions here. Now, of course, you can take this expression and you can factor it and get this one here in principle, but it's not going to be easy. You'll spend a lot of effort in trying to do this particular kind of a thing here. So as I said, this expression is better in providing insight into this particular circuit. It reveals the role of the components in a more explicit manner as compared to this particular circuit. So as an example, let's suppose here that this is 10K resistor, this is 10K here, this is 10K here, this is 10K here, this is 0.1 and this is 0.1 here, right? So if we plug in these values, we'll get a correct value of V0. If we plug it here, we'll get a correct value of V0 here. But this expression allows us to gain more insight into the circuit here. So note, when I have an expression like this, so we see here that R5 plus R6 here, if we look at it, R5 plus R6 is like 20K in parallel with R4. R4 is only 100 ohms. So when you have two resistors in parallel and one of them is much smaller, well, so this particular term is practically going to be R4. In all practical cases, is R4 here. So R4 is 100 ohms, R3 is also 100 ohms. So this whole term is about 200 ohms. And this is 200 ohms is in parallel with 10K. So again, the 10K is not going to do anything. So in effect, R4 plus R3 is going to be only about 200 ohms. And it is in series with R1, which is 10K. So this whole thing here, this whole term here, now we can see is practically equal to R1. This whole term will be equal to VSS by R1. All right, so we can readily see that through an expression like this. Through this also, I'm not saying that you can't do it, but it's harder. So let's look at this particular part here. Well, again, we see that R5 plus R6, you can neglect it. So it's practically R4, R4 plus R3 here. And there's an R2 added to it. So all this term is negligible compared to R2. And then you have R2 by R2. So this is practically equal to 1. And then we come here. So R4 plus R5 plus R6 here. So you can neglect R4 in the denominator because R5 and R6 are much higher here. And R6 divided by R5 plus R6. So both are the same. So there's a factor of 2. So this becomes basically R4 by 2. So what we can see here is that we can readily simplify this expression as VSS by R1. The first term is simply VSS by R1. Second term is about 1. And the last term is R4 by 2. So we could simplify, we could approximate the expression readily using this kind of a structured expression. And now we see that, look, the two most important resistors in my circuits are R1 and R4 for these kinds of numbers which are close to these kinds here, R1 and R4. The R1 is basically deciding the current going into the circuit. And this current and R4 is basically deciding how much voltage is developed. This current that is going in here is practically flowing through R4 here. Of course, there's current division and all that, but practically flowing through R4 here and resulting in the voltage developed here. It's also telling us, look, for example, if let's say for some reason R6 changes from 10K to 11K, or R5 changes from 10K to, let's say, 9K. Well, it's not going to have an impact on V0. My output voltage is not sensitive to this. Not only that, my output voltage is not sensitive to R3. Well, instead of 0.1K, 100 ohms, what if it becomes 150 ohms? It's not going to do much to my circuit here, right? So again, it's not sensitive to R2. This could be 20K and the voltage will still be the same. So when you derive in a structured expression, it allows you to see the roles of the different components. It allows you to simplify and gain insight into the operation of the circuits here. Okay. So, so what we have learned are things that you're already familiar with, the concept of equivalent circuits. That these series connected circuits can be described by a single resistor. Parallel connected elements can be derived by one single resistor. Concept of voltage division, concept of current division. Simple results, but you can apply it in many places and you can use it to your advantage here. Well, the concept of equivalent circuits is not just series and parallel. Look at this particular case. So a little bit of more discussion here to emphasize the concept of equivalent circuits. So let's say I have these three resistors that are here. And basically what we are saying is the following. Let's say you have a node here, three nodes, VA, VB, VC, and we have current IA, IB, IC. So what we are saying is if you look at from the terminals point of view, this circuit, let's say, can be converted into this circuit here. This circuit is equivalent to this circuit. In what sense? Well, if you apply VA, VB, VC here, current IA, IB, IC flows. Well, if you apply VA, VB, VC here, the same current IA, IB, and IC flow. Exactly the same current would flow here. So in that sense, from the terminal current voltage characteristics, the two circuits are similar. And circuit A, and this is circuit B, and B is equivalent to A as far as terminal current voltage characteristics is concerned. So from an external point of view, if you go inside, the two circuits are different. In fact, if you go inside, this circuit has a node here, which you don't see at all in this particular circuit here, right? So, so they're different. But from an external point of view, the two circuits are the same here, and we can derive results like this here. We can derive that if you're given a circuit like this, then you could transform this particular part of the circuit into this part here with an RA, which is given in R2, R3, R1 plus R2, and all these expressions that are there here. And similarly, if you're given a circuit like this, well, you could replace this particular circuit by this one here. You know, so you calculate what is R2, R1, and R3, given RA, RB, and RC here. And so these are also results, you know, to show that how to convert this into this will take you a little bit of time. Apply KVL, KCL, and you know, with a little bit of algebra, you will be able to obtain. But then once you've derived it, if you remember these results, well, it will prove to be useful to you at many places, wherever you see. So these are what we call as a delta Y. I've redrawn it. Delta Y transformation. So you can look, this is like a delta here, this is like a Y. So wherever you see a delta in your circuit, you could transform it into Y if it helps you. And wherever you see a Y, you could transform it into a delta, provided it's useful to you. Okay, so this is a delta Y transformation. We won't use it much, just to explain the concept of circuits, the concept of analyzing circuits with a reuse methodology. So we are saying take small circuits, analyze it, and once you obtain the results, memorize those particular results and deploy it at several places. And you'll find that your analysis will become easier. The other one is, again, a very general methodology. What we are saying is you can solve a complex problem by breaking it up into simpler problems. If I ask you to carry 50 kgs from point A to point B, well, all of you will struggle. But you know that if it's possible, those 50 kgs, if you can break it up into 10 5 kg weights, then you could go from A to B carrying 10 kgs each time, and you will have to do it 5 times. But still, it would be easier as compared to carrying 50 kgs from A to B, right? So solve a complex problem by breaking it into simpler problems. We use that principle in our daily life, and we also use it widely in engineering. Okay, so how do we do that in circuits? Well, let's come back to this problem that we have just talked about. The circuit is given over here, and note, if you look at the expression, yes, it's complicated, but its dependence on VSS is straightforward. In fact, we can write the whole thing, we can write as V0 is K times VSS. And the reason why we can write it in this simple form is that our circuit is made up of linear components. The resistor is a linear element. Mathematically, the relationship is linear. And when you make a circuit and you combine elements which are linear, you get a linear circuit. And a linear circuit has these linear relationships. So I'm not strictly justifying it or proving it, but it's sort of understandable. Linear components, combination of linear components, the circuit is also linear, and the relationships will also be linear. So if I look at V0, V0 is linearly related to VSS. This factor K, of course, is complicated. It involves all these resistors and that you see here. But the dependence on VSS is straightforward. It's proportional. If you double VSS, V0 will double. If you make VSS equal to 0, V0 will go to 0. And that's not just true for V0. If I pick any current, if I pick a current flowing through R4, well, the current through R4 will also be equal to some K4 times VSS. If I pick a current flowing through R2, well, that current will also going to be, I2 will be some K2 times VSS. So this proportionality is for all currents, all voltages. And of course, the K values will differ, right? So this is a useful thing to remember. So, for example, a certain current may be flowing in a certain branch and you would like to make the current double. Well, very simple way of doubling the current would be simply double the voltage here. Well, if that's not possible, then of course you will have to do other things that are there in the circuit. So let's generalize this particular concept here. So in this case, we have two sources here. So V0 is obviously dependent on VS1 and V0 is dependent on VS2. And in this case, we can show, you would expect from a linear circuit, the dependence of V0 and VSN1 will be linear. So V0 is, let's say, K01 into VS1. But V0 would also depend on VS2. These are two independent sources, so K02 times VS2 here. So both these relationships are linear, right? If you double VS1, well, this particular part of the term will double. And if you double VS2, this particular part of the term will double here. So V0 is linearly dependent on VS1 and VS2. Well, we can extend this, but note that this is only true for independent sources. This is not true for dependent sources. For example, if I were looking at I2, well, I2 is, in this case, there's only one independent source. So I2 is simply K2 times 10. So if this 10 volts, I've not put this part here. This is a voltage source, but it's a dependent voltage source. It doesn't come into this particular one. So for example, if I put 10 volt equal to 0, I2 is going to be 0. You can keep this here. For example, you could take it as a homework problem, put this as 0, solve this particular circuit. You'll find the current I2 everywhere is 0. So you need an external independent source of energy to drive currents and voltages into the circuit here. So in this case, I2 will be K2 into 10. Well, let's look at this circuit here. We have three sources here. So in this case, we would expect, let's say if our interest is in current I0. So I0 would be due to VS1, this 12 volt source. I0 will be due to VS2, 24 volt here. I0 will be due to IS3, which is 3 amperes here. So in general, we can write this up. I0 is K1 into VS1, K2 into VS2, plus K3 into IS3. When we derive, this is what the expression is going to look like. And so when we use, so this is what we call it as the superposition principle. So it says that in a linear circuit, the total response is the sum of responses to each of the independent sources acting individually. So I0, the total I0 is I0 due to VS1, I0 due to VS2, and I0 due to IS3 here. So the superposition principle is powerful. It allows us to see contributions of different elements, independent elements that are there in the circuit, independent sources that are there in the circuit. And that's helpful in modifying the circuit, in designing it. And it's also helpful in simplification of the circuit. So let's look at what these arrows indicate, we'll see in a minute. So it allows a complex circuit to be decomposed into simpler circuits. So this is a complex circuit, and we said I0 is K1 VS1, K2 VS2 plus K3 into IS3, right? So it is these terms here. And how do we determine? So if you want to find out I0, you'll have to determine K1. So how do we determine K1? Well, what we can do is we can put VS2 equal to 0 and IS3 equal to 0. So if we put VS2 equal to 0, IS3 equal to 0, let's do that. So we get a circuit. So we put VS2 equal to 0. So we short this voltage source. And we put IS3 equal to 0, which means a current, zero current, which means we open circuit it. And we get this circuit here. Now we solve this particular circuit and we'll obtain a value of I01. And the ratio of I01 and VS1 will give us K1. And note that because we have removed this source here and this source here, the circuit becomes considerably simpler. In fact, by series and parallel resistors, you can find out I01. Similarly, if you want to find out what is this K2 here, Well, what you do is you put Vs1 equal to 0 and Is3 equal to 0. So you get a circuit like this here. Vs1 has been shorted and Is3 here has been open circuited. So again, you get a simpler circuit here. And you solve this circuit to determine K2. And similarly for finding K3, this particular part here, we put Vs1 equal to 0 and we put Vs2 equal to 0. So we short both the voltage sources and we obtain here 3 amperes, and you solve this one. And of course, after solving it, you'll get I01. Note that I01 is only due to Vs1. I02 that you get here is only due to Vs2. I03 is only due to Is3. The total current will be I01 plus I02 plus I03. So what we are saying is, instead of solving one complex circuit consisting of 3 sources, what superposition principle is allowing us to do is take this circuit, break it up into 3 simpler circuits here. One circuit here, second circuit here, and a third circuit here. So, you may say, well, isn't solving one circuit easier than 3 circuits? Well, in general, this one circuit is a complex circuit. So yes, you're doing it, solving circuits, analyzing it 3 times, but each one of them is actually simple. And many times what you would find is that you could simply look at the circuit and write down what is I01. You could look at the circuit and simply write down what is I02. So you could solve circuits by inspection. Sometimes they become so simple that you could readily write down expressions for K1 and K2 and K3. And many times we find then that the analysis of problem becomes much simpler. So obviously there are times when the method may not yield as much advantage as we expected, that even after, let's say, doing it, the circuit is not as simple and therefore it still requires some effort. But it's a useful principle to keep in mind. It allows us to decompose a complex circuit into simpler circuits. And also the final expression that we get is a more structured expression revealing the roles of each components, and allows us to use that expression to modify and design the circuit. All right, so let's wind up our discussion. So we've been talking about various tools for circuit analysis. So this is our toolbox. And what we have is, last lecture we saw a tool called nodal analysis. We also saw mesh analysis. And in today's lecture we saw analysis using pre-derived results, those series equivalent and parallel equivalent and current division and voltage division. So reusing results that have been derived to simplify circuit analysis. And the other one was decompose complex circuits using superposition principle here. All right, so let's stop here and we'll continue and add a few more tools to our toolbox in the next lecture. All right.